Hello everyone. We're going to simulate an ANSYS Maxwell, one of the examples from Chapter 1 of Gross's textbook, the gapped core with a coil. This is example of 1.1, and we're going to set up a 2D model for that in ANSYS Maxwell. So the first thing we'll do, I have it open with a new project. We're going to insert a Maxwell 2D design by right-clicking on the project name in the project tree. It's already set up for a magnetostatic XY cross-section. So I have to draw a background object to contain all the fields, and I have to draw the core and then the two coil sections. So in order to do that, first I want to change the units of the modeler to centimeters, because those are the dimensions given in the textbook. And then I want to draw a rectangle, and this is going to be my background. So I can draw it by clicking with the mouse, but I can also draw or actually enter coordinates in the lower right of the screen. So I'm going to put in an origin of -20 centimeters, tab over -20 for y, and leave z at 0. When I click enter, I'm going to enter the origin point, and then it switches over to dx dy mode, so I can enter the size of the rectangle, and it's going to be 80 centimeters wide and 90 centimeters tall, and when I click enter there, it draws the rectangle big. Okay, I'm going to change the name by clicking in the attributes tree. It's going to be background, BGND, and I'll change the color to white and the transparency to 0.9. And then if I do under the view menu fit all in all views, then I'll be able to see everything. So if I click in the white area, you can see a gray outline for the background. And now I'm going to draw the core cross section to fit inside there. So the next thing I'll do is draw a line, and again I'm going to tab into the lower right corner and enter my coordinates. And I had to make a list of these ahead of time, so I'm just going to type them in. I start at 0.00 and I hit enter. That puts the origin there, and my next point is at 0 for the x, 50 centimeters for the y, and I click enter, and you should see a yellow line drawing up for the left hand side of the core. And I'll just type in the rest of these using the tab or shift tab key to change my coordinates. And each time I hit enter, it's going to add a new point. I will post these points in a comment to this video, so those of you that want to mimic this demo yourself can do so. So again, this core is 40 centimeters wide by 50 centimeters tall, and there's a 0.2 centimeter gap in the middle, which you can see I'm tracing in. 40, 10, 10, 30, 10, tab 30, 24.9, 40, 24.9, tab 40, 0. And now I go back to the origin at 0, 0, and if I hit it again, that's going to terminate the shape. So it's a rectangle with a hole in it and also a little gap. So my name, instead of polyline 1, I'm going to call it the core. I will change its color to be a grayish color because it's going to be iron. So if I click outside all the objects, you can see the core inside a boundary object which contains the fields. Now I want to draw another couple of rectangles to represent the coil cross section. So again, I've got my XY coordinates. The first one inside the core window is going to be starting at 11 centimeters and 20, and then my dx is going to be 1 centimeter because it's a skinny coil winding, and the height is going to be 10 centimeters. So there's a shape. I'm going to call it coil 1, and I'll change its color to an orange because it's going to be copper. So that's the inside part of the coil. I need to draw the outside part, and it's going to be in the negative x side of the coil, so it's going to be -2. The coordinate will be 20, and then my dx is going to be 1 again, and my dy is also going to be 10 as before. And I will call this coil 2, and I'll make the color not orange but maybe yellow. And I click on the outside. So there's my basic shape. It should be reminiscent of the figure drawn in Gross's textbook, for example, 1.1. Now we need to set some boundary conditions and some materials. So the first let's do the materials. I'm going to highlight the project tree. So coil 1 and coil 2 are going to be copper. So I'm going to click on coil 1, and you see it's selected. And in the attribute tree, I have some selections here. Vacuum by default. If I click edit, I get into the materials library. Lots of nonlinear materials, conductors, permanent magnets, and so forth. I want to pick the material copper out of the system library, and I click OK, and now I see that it's copper. Now I'm going to click in the window to select the other coil. I also want it to be copper, and it's in the list because I've already used it in this project, so I'm going to click copper again. The next thing I need to do is put a material on for the core. So in the textbook, the linear core had a relative permeability of 2000. Now if I scroll through here, if you scroll through here, there isn't any existing linear material with a relative permeability of 2000. So I'm going to add one. I click Add Material. The name, I'm going to call it Example 1P1, and the relative permeability, simple means linear. I'm just going to type in the value 2000 and click OK. Those other properties there are for conductivity of the material and permanent magnet properties, and even though this iron is going to be a conductor, it's not of importance for this problem. So you can see I added the new material. It's only valid for this project, and so if I click OK, I've added my linear material to the project, and it is assigned to the core. So I need to do some excitations because I need to put current into the coil, and I also need to indicate that the fields are going to be contained within this background boundary object that I showed. So in order to put a boundary condition around the outside of the problem, I need to go to the Edit menu and select Edges. And I'm going to select the 4 sides of the rectangle, so I click on the top edge and then hold down the Control key and click the other 3 edges. So I'm not assigning the background as a rectangle, but as a hollow box. So I have them all selected. Under Maxwell 2D, boundaries, assign balloon, and there are no parameters to go with this, balloon 1. So how do I know how big to make the rectangle? Well, I want it big enough so that the fields decay to 0 or near 0 by that edge, and I can check it after making a solution here by looking at the field plots. Okay. Now I want to go back to Edit, select Object Modes, because I'm going to select the coil objects and put current on them. So I select Coil 1, Maxwell 2D menu, Excitations. I want to assign a current. Okay, so I get a name, Current 1. It goes with Coil 1. And I'm going to put in a value of 2400 amperes and leave the reference direction positive. So the problem posed in the textbook had 200 turns and 12 amps. So in a finite element software package, you don't use amps and turns separately. It's ampere turns. So even though the units are amps here, I want the 12 amps times the 200 turns, so I get 2400 amps. So it's the same as 1 amp in one term, or excuse me, 2400 amps in one turn is the same as magnetically as 12 amps in 200 turns. So let me select the other coil, coil 2. I'm going to edit under Maxwell 2D, excitations, assign a current. It's current 2. I'll call it 2400 amperes, but I'll put it in the negative direction. Okay, so on the orange coil, current comes out of the page, and on the yellow it goes into the page. All right, so there are no moving objects in this problem, but I do want to set up a calculation of the inductance. So under the Maxwell 2D, parameters, assign, a matrix. But you can see when you pull up that menu, there's also a force and a torque selection. So I click the matrix, and I'm going to include current 1 in the matrix, and the return path is current 2. So what that's going to do is calculate an inductance, a 1-by-1 inductance matrix for current flowing into coil 1 and coming out, through coil 2. So at this point, I'm ready to solve the problem. If I'll expand my project tree, under analysis, I want to add a solution setup. And this is going to be okay. We don't have to do anything here. But what Maxwell is going to do is automatically build a mesh and solve, refine it to get an accurate solution of the magnetic fields. So I expand my tree under the project tab. I right click on setup 1, and I'm going to do analyze. It's making me save the project, so that's fine. Okay, you can see in the progress bar in the lower right, in this case it solved so fast that we didn't really see any updates. But if I want to look at some of the results, I'll click on setup 1 and look at the convergence. So I can see that there were 4 passes. It started with 174 triangles, ended with 544. Let's look at the matrix solution, and I get 0.05247 millihenries. See that value here. So that's not the value that was in the book. Okay, but to see how to convert that, I'm going to bring up a MathCAD sheet. So I have 200 turns, and the depth is 10 centimeters or 0.1 meter. Okay, so these are parameters for my actual device. The finite element inductance calculation was 0.05247 millihenries, and that's per meter. That's per meter depth into the screen. So my depth is only, in the real device, it's only 0.1 meters, so I have a scaling factor. I'm going to do 0.1 meters over 1 meter. So when I convert to the actual inductance, I'm multiplying by D, and I'm multiplying by n squared. Because when I set up the problem, it assumed that there was just one turn, and it assumed that I had 2400 amps in one turn. Really, I have 12 amps in 200 turns, so the inductance is going to be higher. And what I get then is 209.9 millihenries, and that compares to 189.2 millihenries calculated in Gross's textbook. So why the difference? Well, there's some assumptions made in a hand calculation that aren't exactly right. So let's look at some of the plots. Under field overlays, well, first I want to click in the modeler window and hit Control A to select everything. So under field overlays, it's instructive to plot the mesh for everything. And so you can see that this is how Maxwell broke down the problem geometry. And the smallest triangles are near where the air gap is, and there are other. The medium-sized triangles are next to the coil, and then the bigger ones are outside, near the boundary. Other plots that I can make are under fields. Let's plot the magnitude of the field that's mag B for all objects. And you can see in the inside corners there's a high density of the flux. And then if you can also see, I'm going to zoom in a little bit. Look at the light blue areas right by the gap there. That's called fringing, and it's something that's not covered, not included in a hand calculation. So a couple of effects here that the finite element solution can handle that usually are not covered in a hand calculation. So another thing there's several other plots you can make, flux density lines, the current density, and so forth. So I encourage you to experiment with some of those. I want to change, before we're done here, I want to change the core material to something that's nonlinear. So I had example 1P1, which was a linear permeability, relative permeability 2000. I'm going to add another material. This is patterned after example 1.5, in which Gross changed the linear material to a nonlinear one. And then the relative permeability is not going to be simple, but it's going to be nonlinear. Okay, so I click on this button to have the BH curve, and I can enter a table of H and B values. So again, this is following a translation of the graph in Gross's textbook, which was figure 1.6. Okay, so again, I will post these points as a comment to the video, but the origin is at 0, 0. I have 400 amps per meter, 1 Tesla, 600 amps per meter, 1.15 Teslas, 1200, 1.32. If you were really going to do an analysis of an actual device, you could use more points and get a more accurate entry, but I'm just trying to illustrate some things. What's the effect of a nonlinear material on the inductance, and you can see that it saturates. And I've got just a few points defining the knee of the curve, but good enough for our purposes in this example. So I click OK, and notice that my material changed, and I have a message down here that the solutions have been invalidated. I could undo that change to recover it, but my field plot went away. So what I need to do is analyze again. And it takes longer to solve this time, or at least you can see a progress bar update. You can see some changes to the magnetic field intensity. And then if I go to the setup convergence, and see it needs more triangles. We had 544 before, now it needs a couple hundred more to get a good solution. And I go to the matrix output, and I get 0.048261, and that's millihenries, and that's per turn. So again, if I wanted to see what the impact is, I can edit this in MathCAD. It's 0.048261. Let me make sure. Yes. So my result now is 193 millihenries, so it's a reduction. So saturation in a core either reduces the inductance, or if there isn't any effective saturation, it'll keep it the same. You'll see a lot more the features in Maxwell when you do the second lab, but this is just an illustration to show you how it can improve the accuracy over textbook calculations.